Let's solve this geometry problem carefully and find the missing length, x. We have two vertical segments standing on the same horizontal base. The vertical segment on the left has length 15, and the vertical segment on the right has length 30. Two diagonal lines connect the opposite endpoints of these vertical segments, and they intersect at point P. From P, we drop a perpendicular to the horizontal base, meeting it at H, and the length of this perpendicular is x. We are also told that the horizontal distance from the left endpoint to H is A, while the distance from H to the right endpoint is B. Our goal is to determine x. Now, the nice thing about this problem is that we do not actually need to calculate A and B individually. Instead, we can use the tangent of the two angles created by the diagonals. Let's start with a diagonal that rises from the left bottom point toward the right top point. On the right side of P, call the angle between this diagonal and the horizontal base alpha. Look at the small right triangle containing P, H, and the right bottom point. In that triangle, the side opposite alpha is PH, which has length, x, and the side adjacent to alpha is HR, which has length B. Remember, for a right triangle, tangent of an angle is the opposite side divided by the adjacent side. So we can write tangent of alpha as x divided by b. In spoken form, that is tangent alpha equals x divided by b. Now, we are going to look at the larger right triangle formed using the entire horizontal base and the left vertical segment. The vertical height of that triangle is 15, and the entire horizontal base is made from a plus b. Therefore, using the same tangent rule, tangent alpha is also 15 divided by a plus b. Notice something important here. Both expressions describe the tangent of the exact same angle alpha, so they must be equal. Therefore, x divided by b equals 15 divided by a plus b. Now, let's rearrange this equation in a useful form. We want x divided by 15 on one side, starting with x divided by b equals 15 divided by a plus b. We can cross-multiply to get x multiplied by a plus b equals 15 multiplied by b. Now divide both sides by 15 multiplied by a plus b. This gives x divided by 15 equals b divided by a plus b. This will be our first equation. Keep that relationship in mind because we are going to use it again in just a moment. Now, let's move to the other diagonal. This time, consider the angle beta formed between the other diagonal and the horizontal base on the left side. Look at the small right triangle formed by the left bottom point, H and P. The side opposite beta is PH, which is x, and the side adjacent to beta is the horizontal distance from the left bottom point to H, which is A. So, using the definition of tangent again, tangent beta equals x divided by A. Now we switch our attention to the large right triangle on the right side. The vertical height there is 30 and the complete horizontal base is still a plus b. Since the angle beta belongs to the same diagonal, tangent beta can also be calculated as the opposite side, 30, divided by the adjacent side, a plus b. So we have tangent beta equals 30 divided by a plus b. Since both expressions represent tangent beta, we can set them equal to each other. Therefore, x divided by a equals 30 divided by a plus b. Let's rearrange this one just like we did before. Cross-multiplying gives x multiplied by a plus b equals 30 multiplied by a. Dividing both sides by 30 multiplied by a plus b gives x. divided by 30 equals a divided by a plus b. This is our second equation. Now pause here for a second because this is the key idea of the entire problem. We have one equation telling us that x divided by 15 equals b divided by a plus b, and another equation telling us that x divided by 30 equals a divided by a plus b. We could try to solve for a and b separately, but that would be unnecessary. There is a much cleaner move. We simply add these two equations together. So, on the left side, we have x divided by 15 plus x divided by 30. On the right side, we have b divided by a plus b plus a divided by a plus b. Now, look carefully at the right-hand side. Both fractions have exactly the same denominator, a plus b, so we can combine their numerators. That gives b plus a divided by a plus b. And because b plus a is the same quantity as a plus b, this becomes a plus b divided by a plus b, which equals 1. This is the beautiful cancellation that makes the problem so simple. So now our equation is x divided by 15 plus x divided by 30 equals 1. Let's simplify the left-hand side carefully. The common denominator of 15 and 30 is 30. So, x divided by 15 can be rewritten as 2x divided by 30, because 15 multiplied by 2 gives 30. Therefore, we have 2x divided by 30 plus x divided by 30 equals 1. Since the denominators are the same, we can add the numerators. 2x plus x gives 3x, so we get 3x divided by 30 equals 1. Now, simplify 3x divided by 30 by dividing both the numerator and denominator by 3. 30 divided by 3 is 10, so we get x divided by 10 equals 1. At this point, the final step is very straightforward. If x divided by 10 equals 1, multiply both sides by 10. That gives x equals 10. So, the perpendicular length from P down to the horizontal base is exactly 10 units. Notice how we never had to find A or B individually. The two tangent relationships allowed those unknown horizontal distances to disappear when we added the equations together. That is the central trick here. Identify the same angles. Express their tangents using both the small and large right triangles, rearrange the relationships, and then add them so that a plus b cancels naturally. This is a really useful geometry technique whenever two intersecting diagonals create similar right triangle relationships and an unknown height appears in both. If that key cancellation made sense to you, take a second to like the video. And if you enjoy these geometry problems, subscribe for more. And I'd also love to know in the comments whether you spotted the idea of adding the two equations before I revealed the final step.